so Drew and I are sort of have a combined talk, and so we were just, for simplicity, might just go through the whole time, which is whatever the time is times 2, and then take all our questions at the end, which maybe will be efficient. So the first part of this work that we're talking about is a paper going into the Deep Sea Research Special Issue led by our postdoc, Kate Adams. And so Kate was on the last cruise and has done most of the analysis for this. She has since taken another permanent position, but we're still trying to submit this paper. So we've been thinking about the types of questions that we can ask with the vast data set we have in hand, not just from the Mesobob cruise, but from the last sort of many years of combined experiments. And it seems like the types of questions we're asking fall into 2 types of categories. On the left-hand side, we're trying to ask questions about what is the basic phenomenology of what's happening here, what's the interesting physics, what are the processes happening. And on the right-hand side, we're trying to sort of find the combination or the parts of those things that can help us directly assess model parameterizations and improve them, ideally for improving forecast models. And so the bit that we're going to start out talking about are just these 2 things here in the box, which is using the data in hand, can we assess, sort of a theme of the morning, how well do 1D, one-dimensional mixing parameterizations in the upper part of the ocean correctly or incorrectly represent the rate at which heat is sort of mixed in and out of the ocean over the course of a diurnal cycle or a meso event. And the second is we've sort of been focused, especially for Syria, on the relative importance of small-scale lateral density gradients associated with the submesoscale. And so the second question is, to what extent do those things mediate or not the heat exchange into and out of the atmosphere? Do they pertain to that process? So the data for this paper and for the first part of our talk comes from the 2015 Syria cruise. And so the location of which is shown on a sea surface salinity map in the upper left. And so there's 4 different types of data that we're putting together here. And so the idea is to use the combination of these 4 different data sets to assess not only the one-dimensional evolution and time of the upper ocean mixed layer, but the fact that we have 4 different concurrent measurements, scale separated by different lateral distances, to assess the relative role of lateral gradients in the one-dimensional processes. So the first one is from the 18 North mooring. And so here's some data shown from the 18 North mooring on the right, just over the time period in which we had shipboard measurements. And so you could see, if you look, for example, is there a pointer? Yeah, that there's arrival of a thin, fresh near-surface layer during this period. There's often a subsurface temperature max below that layer. It's reasonably sunny most of the time, and the wind stress is sort of increasing toward the end of this period. That there's velocity you can see here that is often concentrated within the thin surface layer. So there's strong shear that you can see at the base of that surface layer. The shipboard measurements took place. The measurements, go back. The shipboard measurements took place not too far from the mooring. And during the time period described here, the ship was going in a little triangle over and over and over. So here's an example of the ship moving in a triangle. The main tool being discussed here for the density measurements is the fast CTD operated by our group at Scripps. And so basically it's a sort of long torpedo-shaped CTD that goes up and down at about 5 meters a second. So it gets very rapid profiles, very high horizontal resolution. So as the ship went round and round in this triangle, you can sort of try to see both small-scale lateral gradients and time evolution at the same time. If you repeat the triangles frequently enough, you can see a lot of the same phenomena you saw in the shipboard measurements, or in the mooring measurements. There's a thin, near-surface, very fresh layer, strong shear often at the base of that. We also had microstructure provided by Emily and Jonathan, and you can see sort of strong turbulent dissipation right often at the base of the surface mixed layer. Next tool is this wire walker, which is Drew and Rob Pinkles, and it is powered by surface wave buoy with ratchets this thing down and then it floats back up. It was released and drifted along this black line here, so it went through the area of the shipboard measurements. Here it is, and it can see a lot of the same features, but it also has it makes clean measurements, unlike the ship, which has a surface weight contamination by the ship propellers. You can see clean measurements of turbulent dissipation rate of temperature and shear and stratification all the way up to the surface. So you can see the surface mixed layer in much clearer detail. And then finally, Jonathan Nash from OSU the sound isn't on, has his little autonomous kayak, which was going in little boxes. And so it was making simultaneous triangles around the ship triangles so you can see lateral gradients. And so these triangles, for example, were made at the same time, and you can see the presence in just like a kilometer or so, the presence of significant lateral gradients in density, salinity, temperature over very small lateral scales. And the value of doing this at the same time is you can deconvolve the rate of change in time from spatial gradients. Okay, so the first question was, what can we learn from these measurements about one-dimensional mixing rates? And so one of the interesting things that you can see, there just highlight a couple things for this talk, is that when you have, we're going to look at an example here near the end of the record. Top panel here shows the wind stress, which is picking up toward the end of the record. As the wind stress picks up, the surface mix layer deepens considerably. But one of the interesting things is that as it deepens, momentum and buoyancy do not appear to be mixed downward at the same rate. And so to see that more clearly, I've made a blow up of this sort of just the last couple of days of the record here. This top panel here shows stratification. So this is n squared. And you can see the mix layer initially has this very sharp base in the mix layer, high stratification, and it is diffusing and moving downwards as the mix layer deepens. The bottom panel is shear, so shear squared. And the white contours here are the stratification from the upper panel. So you can see the shear is situated above the peak in stratification. They are not co-located. And if you compare them more quantitatively by calculating a Richardson number, that's the black line here. So this everything where you see black lines has a Richardson number which is a quarter or lower. So these are critical to shear instabilities. So the shear all sits just is all housed just above the depth in which the Richardson number is critical, which is above the depth of maximum stratification. So one of the things that's interesting about that sort of interesting physics thing, relates back to Sutana's talk in and of itself, but one of the interesting things about that is if you run KPP, which is what is HICOM and a lot of models use as their mix layer parameterization, KPP has this bulk mix layer algorithm. The diffusivity for buoyancy and momentum is locked to have the same vertical structure. So KPP, when you run it with the same wind forcing, here's a KPP model run. The mix layer not only deepens too much, which maybe is due to other issues, but the shear and stratification are co-located. They have the same vertical structure, which is not consistent with our observation. So that's interesting thing number one. Interesting thing number two about 1D mixing is that one of the things that you see, this is sort of a quasi one-dimensional process that several people talked about earlier. The wind blows on the surface mix layer. It starts to move in these inertial oscillations because it's a resonant frequency in a rotating planet. And you can look at this. This is from the mooring data here during the period of our measurements. If you take the mooring velocity from the upper bit of the ocean, you can run the same type of slab model that Mani talked about, or somebody talked about earlier, where you just sort of force it with the resonant wind stress. And you can see, so here's the observed velocity, a slab model velocity, and a bandpass velocity. So the black line is sort of a bandpass velocity around the inertial period. One of them is what you get from the slab model, and the red is the residual. So some of the strongest mixing events that we saw at the base of the mix layer were not driven from the surface by surface wind stress or convective loss, but a lot of the mixing at the base of the mix layer was driven by inertial shear. And just for an example, here's one period where there's a superposition, it appears, of a residual which may be tidal shear as well as the peak inertial shear. During this time, you can see the strong shear at the base of the mix layer is here. Strong turbulence that's co-located with that shear. This is during a time of low winds and sunny sunlight. And so the turbulent heat fluxes here are not driven from any sort of forcing at the surface. They're driven by this inertial shear. There's associated upward heat flux of 15 watts per meter squared into the surface layer. So the next question here was, for these one-dimensional processes, not only are they consistent with what we know about how 1D mixed layer models work, but do any of the sub-mesoscale density gradients that we've been sort of obsessed with for the last few years have any relevance for any of these processes? And so one way they can have relevance is continuing on the near inertial oscillations. So because we had co-located measurements, you can look at the near inertial component of the velocity from several simultaneous measurements and see if they are all in phase. If you have a large-scale storm, you blow it over the mix layer at a whole bunch of places that are only a few kilometers apart. They should all be moving together. if there are lateral density gradients or lateral vorticity gradients, they may get out of phase with each other. And when they get out of phase with each other, they start to converge and diverge at the inertial period, pump the base of the mixed layer, and make downward radiating internal waves. And so that's a way to get energy out of the mixed layer where it can mix at depth. And so just as one example of this, here's the near surface inertial component of velocity from the mooring in light blue, from the bandpass version of that in purple, and from the wire marker measurements in black. And you can see the wire marker measurements are out of phase. They're only 4.6 kilometers away, but the inertial motion at the wire marker and that at the mooring are only 4 kilometers away, are out of phase with each other. The wind stress has much larger scales, presumably, than that, but somehow the density or vorticity gradients have let them get out of phase. And so that can be an important way that the lateral gradients affect the evolution of shear in the mixed layer and hence its associated mixing. I do not remember offhand. That may come up in the next slide. The second thing that can happen, the second effect that small-scale lateral gradients can have is just due to exactly what Amit just asked. If you have differences in the stratification at short lateral distances away, this is also one of the things Eric was just talking about, the rate of exchange of heat from the atmosphere to the ocean and back can be different, one place versus another. And if there's any nonlinearities in that process and the rate at which the atmosphere says, here, have some heat, I'm going to take it back, have some heat, I'm going to take it back. If there are nonlinearities in that, then using the average mixed layer depth does not give you necessarily the same answer you would get if you do the exchange with the full sub-mesoscale density and stratification fields. So to give you 2 examples of why you might believe that that would be important, here is the wire marker drift, and there's 2 things plotted here. This line here is near surface density, and so this is just to point out that as it drifts, it's drifting through a variety of sub-mesoscale density gradients. And so it goes from sort of green to red, which is about a kilogram per meter cubed. This is a noticeable density gradient over not very large scales. This color here, which is a little bit washed out in this projector, is the measured near-surface turbulent heat flux upwards or downwards towards the atmosphere. This is the heat flux into or out of the ocean, essentially measured in just the top couple meters. And it's a few hundred watts per meter squared, but it changes not only by magnitude by a few hundred watts per meter squared, but actually sign as you move into and out of these different sub-mesoscale density areas as the sort of process of exchange back and forth is different. So the gradients can be quite substantial on very small scales. And one way to evaluate the importance of that in an integrated sense that Kate did, and this is going to be sort of a segue into Leah's talk later in this session or maybe next, is she said, okay, well, let's take 3 simultaneous profiles that were taken at the same time of day, the same point in the diurnal cycle from 3 different measurements, 4 kilometers apart each, the wire marker, the mooring, and the ship, and initialize a KPP run with the same wind forcing, same surface incoming heat flux, which with each of these and see if they diverge. And one way to assess that to see if they diverge is to kind of do a poor man's kind of halfway coupled model, which is that she let the air sea fluxes be governed by the model evolved SST rather than sort of fixing the SST, and that lets the model sort of let the evaporative, the latent heat respond to the changing model mixed layer heat content. And so if you initialize a model with these 3 profiles, let it evolve in time, here is just sort of the cumulative net heat flux from the mooring. These 3 are the cumulative heat flux into the ocean for each of those 3 model runs. If you just look at the differences between them, these are just 3 things initialized with 3 different temperature profiles. You can see a changing rate of the cumulative heat flux. This is in joules per meter squared. There's a 10 to the 5 joules per meter squared. Over a 2-day period, they have started to diverge on the order of about 15% of the average value between things which are only based upon 4-kilometer apart segments. So small differences in sub-mesoscale ocean gradients can lead to different exchange rates with the atmosphere on small scales.
What do you do?
That was just held fixed. So this is kind of a, right, well, but that's a good idea. Okay. Moving